Okay, in the last few videos, actually 2 videos, we first took a look at the Euler-Lagrange equations, which leads to Newton's second law. And we also took a look at one example where we considered the Lagrangian of a harmonic oscillator, and we derived the well-known equation describing the harmonic oscillator. In this video, I want to describe actually the problem of a particle in the Earth's gravitational field. So let's start. So remember that the Euler-Lagrange equations are given by d by dt partial L partial x dot, and this is equals to partial L by partial x. And L, if you remember, is the kinetic energy minus the potential energy. Now, in the T is the kinetic energy, and it's just 1/2 mx dot squared. We usually consider m to be a constant, so it doesn't change in time. So, yes, and the potential energy is in fact the mass of the particle times the gravitational acceleration times the height, or in this case actually we will use the letter x to denote the height. But before we proceed with calculating the equations of motion, I would like to motivate this equation actually. So if you remember, the potential for a particle in a gravitational field is actually minus g times capital M times small m over r. Now, where r is the distance from the center of the Earth to the center of the particle, capital G is the gravitational constant or Newton's constant, and capital M is the mass of the Earth in our example. So what we can do is we can write capital R, small r, to be capital R plus x. What do I mean by that? Basically, if you have the Earth like this, then we have a distance capital R from the center of the Earth to the edge of the Earth, and then we have another x which stands for the height of the particle. So the reason why I do it is because this capital R is actually a constant. So if we plug this into our expression for the potential, we get capital M over small m over r plus x. And now what we can do is we can write this as minus g capital M small m over r times 1 plus x over r. The reason why I do this is because if x is much smaller than capital R in this expression here, then I can use the binomial expansion, an approximation, which is roughly minus g capital M over small m over r times 1 minus x over r. So what we get is that this is equals to minus g m over small m over r plus g capital M small m over r squared x. And now if you note this expression here is just a constant, and we say that this is equals to g. If you plug in numbers for our Earth and for the gravitational constants, you will find that, without the m. So we write the m here. So if you do this for the Earth, then you will get roughly 10 meters per second square, or roughly 9.81 meters per second square. But if you recall now, look at the Euler-Lagrange equation. The Euler-Lagrange equation is dependent upon, the derivative of the Lagrangian is taken with respect to x. And if you look here, we have one term which is constant and one term which contains the x. So if I differentiate this with respect to x, this first term will fall away, and what remains is that partial L by partial x is just mg. That's it. Partial L by partial x. Actually you get a minus. Because this is the potential. This expression over here is the potential. This expression here is the potential, and we are taking the Lagrangian is the minus of the potential. So you get a minus, you pick up a minus sign. So we can now calculate the Euler-Lagrange equation of motion. So we write them down again. D by dt of the kinetic energy is equals to d by dl by dx. Let us calculate. This is partial L with respect to x dot. And now this is just, recall that the kinetic energy is just m x dot squared half. So if I differentiate this with respect to time, I get t dot is equals to m x dot. Oh, sorry. I get the partial t by partial x dot is m times x dot, right? And yes, so we get that the Euler-Lagrange equation reduces to d by dt of m times x dot, because the L here is only dependent upon the kinetic energy when we differentiate with respect to x dot, and this is equals to minus mg. And now here we get the usual equation. We get m times x double dot is minus m times g, or we have x double dot is minus g, which basically says that the acceleration is equals to the gravitational acceleration. So as you can see, we've now calculated the equations of motion for a particle in the Earth's gravitational field, which is very close to the Earth, so the acceleration is almost constant. So so we calculated that the acceleration is just minus the gravitational acceleration. So yeah, that's it. Thank you for watching.